So let us start today's lecture by reviewing the Fourier transform formulae that we derived in the last lecture. So if you have some function, then we can write this as, okay, since this is going to be a wave function, it'll have some time dependence. So, and we can write this as here is the Fourier coefficients. Now we can introduce, instead of k and omega, energy and momentum. So we can use the formulae that omega is related to the energy in this way, and the wave number k is related to the momentum, like so. And then we can define a Fourier coefficient A, which now depends on P, to be given by the Fourier coefficient, which depends on K, divided by square root of H bar. So if you use these definitions, then we can rewrite our wave function as so now we have energy and momentum in our exponential, and the integration is over P. And its Fourier transform now is given by So far we have been in one dimension, but it's useful to write the generalization of the wave function to three dimensions. For some of the lectures in the future, we will still be sticking to one dimensions, but eventually we want to go up to a higher dimension. So when we do that, these expressions will come in handy. So if you had a three-dimensional system, then it'll depend on three coordinates, x, y, z, and a time coordinate, and then the Fourier transform formulae would be given by. So there will be a Fourier transform for every direction, so there would be a cube here, and then there will be three integrals, and we'll have a of p, but now p is a three momentum, and then we have e to the power I by h bar, and now inside the exponential argument we'll have vectors dotted, and then this will be a volume integral in momentum space. And similarly, the APs would be given by a similar formula, but now this now has a minus sign. So these are the generalization of the Fourier transform formulae to three dimensions.